This is Tyagi, and welcome to our YouTube channel, Learn Comparative Programming with CodeChef. If you're into data structures and algorithm, then this is a one-stop destination for you. Every week, we're going to post videos about problem-solving paradigms, live problem-solving sessions, and much more. So if you're interested, here's a little reminder for you to hit that bell button and subscribe button. So let's get started. Firstly, a bit about myself. My name is Tyagi. I'm a pre-final year student at IIT Delhi, and I'm a comparative programming enthusiast. I have experience in AI research and software development, and my favorite hobbies include playing poker and CSGO. Okay, so the question that we're going to do today is find XOR, and it's an easy to easy medium problem, and the difficulty rating that I have assigned it is 1800, and the prerequisites of this solving this problem is bitwise operators. So let's get into the workflow of how things are going to go. So firstly, we're going to understand the problem statement. So this will be an interactive problem. So I'm going to first tell you about a bit about interactive problems, and then we're going to build some intuition using the number of queries that we're allowed in the interactive problem. Make some observations imperative to solve the problem, and then transform those observations to fit the allowed constraints. And finally, we're going to look at some working pseudocode and the implementation details. So let's get down to the question. So this is the question. So given a sequence of integers, we're not given a sequence of integers. There's a sequence of integers which the grader knows in the compiler, and that is a1 to an. We do not know this sequence. Our task is to find the value of the XORs of all of these combined. So this operator is the bitwise XOR operator, and this is a bitwise operator. That means it operates independently on bits. So we have our objective is to find the value of a1 to an XOR. So in order to find this value, we may ask up to 20 questions, and in each question we're going to choose a value k, and we're going to give the grader k the value, and then when we give this value to the grader, and this k belongs to 1 to 10, 2 into 10 to the power 6, when we give this value, then the grader replies with a number, and that number is basically the sum of the individual XORs with that number k. So the answer that the grader will give us will be a1 XOR k plus a2 XOR k plus a3 XOR k and so on till an XOR k. The constraints given are, there are t test cases 1 to 100. The value of n lies from 1 to 10 to the power of 3, and ai lies from 1 to 10 to the power of 6. Okay. So before starting, if you've understood this problem, then sure, let's go ahead. But if you haven't, I'd suggest that you pause this video for a while and like read this problem and try to solve it once. And if you can't, come back to the solution, and we're gonna start ahead. So okay, so firstly, let me explain a bit about parity. I'm going to explain some things that I'm going to use throughout making this video, and these things are firstly parity. So what do I mean by parity if two people have the same parity? So what I mean by parity in this context is basically whether they have the same remainder when divided by 2 or not. So basically what I mean by saying that 5 has the same parity as 3 is basically 5% 2 is equal to 1, and 3% 2 is also 1. So I can say that 3 is equivalent to 5. So this is an equivalence relation in terms of parity, and I'm going to keep using this relation. And what this means is on the left hand side, whatever the number is, that has the same remainder modulo 2 value as the same as the RHS mod 2 value. So for example, 3 and 5 are equivalent, and 1 and 5 are also equivalent, but 1 and 4 are not equivalent. So this is not true, but 2 and 6 are equivalent because both of them give the remainder of 0 when divided by 2. So so we talked about parity and this equivalence relation. Just keep in mind these two things. So let's talk about bit shift operators. So bit shift operators operate on bits. So whenever I'm operating, for example, if I say, so there are two types of bit shift operators, the left shift bit shift operator and the right bit shift operator. I'm going to talk about both of them. So if I say that I'm bit shifting the value 2. So I'm actually not, this operator is not operating on 2. It's operating on the bits of 2. So whenever I have this kind of bit shift operator, I always have to visualize it in terms of whether it's this or it's XOR. We're going to talk about XOR later, but whether it's this or XOR, we need to remember that it operates specifically on the bits independently and not the number itself. So if I want to find out the value of 2 left bit shift operator of 1, then what I mean is key, I'm going to write this as 1 0 and then bit shift operator 1. And what this will do is basically it will shift, it will add one more bit. It will shift all the bits to the left. So the answer to this will be 1 0 0, and which is equal to 4. So similarly, if I am doing 2 1, right, bit shift operator, so it will shift. So I'm going to write this as 1 0 bit shift as 1. And what this will do is this will remove the last bit that 2 had, which is equal to 1, and it will only be left with 1, which is equal to 2. So this is binary. This is binary form. Okay. So let's move ahead. What this basically does is, if I'm writing a number a, bit shift I, right, bit shift I. So what this means is basically what I'm doing is I'm multiplying a with 2 to the power of I, because I zeros will be added ahead of a in its binary form. And what that essentially means is that a will be multiplied by 2 to the power of I, strictly speaking, in mathematical terms. Simply, if I do this operator on I, so what I'm left with is a divided by 2 to the power of I, because I bits from the right side, from the least significant bit to the I bits. So those bits will be destroyed, because those bits will be shifted and destroyed. And what we are left with is basically a divided by 2 to the power of I. So let's move on. Let's talk about a bit about XOR operator. So XOR operator's truth table. Let's take a look at this. So here we have the truth table. So we have A and B. Suppose these are the two bits that we're talking about, and C is the XOR operator of A and B. So there are four cases: 0 0 0 1 1 0 and 1 1. So what the XOR operator does is it's an exclusive OR, and by definition, what we have defined it, this truth table is defined. We have defined the operation what XOR does. So don't ask like the logic, where did this logic come from? This logic is there. So we've defined XOR in this way. So the truth table that we've defined for XOR is that A and B, if both are 0 or both are 1, then it's a 0. But if either one of them is 1, then the value is 1. The answer is 1. So as you can see, so in case of A and B are both are 0, it's a 0. In case A and B both are 1, it's a 0 again. But in the case that B is 1, A is 0, or A is 1 and B is 0, the answer is 1. One more thing that I want you to, one more angle that I want you to look at this at with is that whenever we're XORing with, so there are two cases. No matter the value of A, if we're XORing with B, then we can take two cases. Firstly, B has a value of 0. So let's check out these two cases. These two cases. So whenever the value of B is 0, the value of A doesn't change. So A XOR B when B is 0 will be A, which is 0 in this case. A XOR B when B is 0 will be A, which is 1 in this case. So this never changes. So this is the thing to remember. Bit stays the same when XORing with 0. This is one thing to remember. And the reason behind this is that if you XOR A with 0, any number with 0, this is A is not just a bit, any number with 0, then the answer is that number itself. So it's basically the self identity. It's the identity operator when one operator is 0 and I'm XORing it with it. In the second case, when B is 1, let's talk about this case now. So in the second case, when B is 1, so there are two cases, whether A is 0 or A is 1. And in this case, if A is 0, then A shifts the bit that we're talking about when XORed with 1, it flips. It became 1. In this case, when the bit was 1 and we XORed it with 1, it became 0. So the bit actually flipped. So we can see it's 1 and 0. It is not the value of A. It is not A. It is basically the opposite of A. The bits flipped. So one more thing to remember is that bits flip when you're XORing with 1. This is one thing to keep in mind while we're solving this question, because this will help us in our journey to solve this question. So one more thing that I want to talk about, that XOR is commutative and associative. What I mean by commutative and associative is that XOR operator doesn't only work on two bits or two numbers. So it can work on many numbers. For example, in the case that we're given, in the question that we're given, we have to calculate the value of A1 XOR A2 XOR A3 till XOR AN. And so the order in which I place them doesn't matter. I can place them in any order that I want, and the answer will still remain the same. And that is what I mean by the XOR operator being commutative and associative. So it doesn't matter, as you can see here, A XOR B XOR C. So it doesn't matter if I XOR A and B first or not. It doesn't matter if I XOR A and C first or not. It doesn't matter if I XOR B or C first or not. The answer will be same in each of the cases. This is one more thing to keep in mind. So let's do an example. So if I do 1 XOR 2, so as I told you, the XOR is also a bitwise operator. So whenever we are using a bitwise operator, we always have to think in terms of bits. So we're going to have to write the binary expansion of 1 and 2. So the binary expansion of 1 is 0, 1, and the binary expansion of 2 is 1, 0. And in this case, when we XOR both of these numbers, so the way that it works is the 0th bit gets XORed with the 0th bit. So the bit XOR is independent in this case. So the 0th bit is 1 and the 0th bit is 0 in this case for 1 and 2. So these two bits will XOR and will get the 0th bit of this answer. And as you can see, 1 and 0, the answer is 1. The answer is 1. So the 0th bit is set. Whenever I say that the term that this bit is set, what I mean by that sentence is that that value is 1. That bit is 1. So whenever I say that a bit is set, what I mean is that bit is 1. So this bit is set because 1 XOR 0 is 1. So all the 0th bits, all the bits XOR independently for a number. And this is an important thing to note down. So 0 XOR with 1 is again 1. So these bits get XORed and the value that we're given is 1. So let's go ahead and do for 3 of these values. So again, as we have seen, as we have talked about, that the order doesn't matter. So I have written it in the same order: 0, 1 XOR 1, 0 XOR 1, 1, and I'm going to XOR first these two values. And as you can see, we have already XORed these two values, and that value is 1, 1. And when we XOR it with 1, 1, we know that that value is 0, 0, because one bit is set in the 0th bit, one bit is set in the 0th bit, and we know that 1, 1 gives us a 0. Again, the same in the second case. 1, 1 is 0. So the answer is 0 in this case. So this is a bit about the commutative property and a bit about XOR. So let's talk about one claim that we're making, and that claim is, so if we're talking about A to Z bits, so suppose we have any number of bits, let's name them A to Z, and these are bits. That means A to Z can only hold values from either 0 or 1, one of these values, not between them, but either 0 or 1. So if you want to talk about the XOR of all of these combined, so if you want to talk about answer, if you want to comment on answer, what that answer will be if we XOR all of these bits together, then obviously, because these are bits, the answer will always lie from 0 to 1. Then we know our claim is that the answer of 0, the answer of these bits XOR together is 1 only when the number of ones from A to Z is odd. Otherwise, it's 0. So why do I say this? Why is this true? So let's talk about two cases. When the number of ones are even and number of ones in from A to Z are odd. Okay, so that means that there will exist some number I such that the number of ones are 2i. There will exist such some I such that the number of ones are 2i plus 1. So this is just another way of saying that this number of ones is even, number of ones is odd. So 2i ones are present out of these A to Z bits, and 2i plus 1 bits will be 1 will be set out of these A to Z bits. So let's talk about in this terms when the number of ones are even. So for 2i bits, what I can do is, since we've talked about that the order doesn't matter, I'm going to write these ones together. I'm going to group them in groups of 2 and write them together. So we'll have I of these groups present and the rest will be zeros. And what I'm going to do is I'm going to XOR each of these pairs that I've made. So I'm going to XOR 1 with 1, XOR 1 with 1, XOR 1 with 1, XOR 1 with 1 of all the I cases that are present. And what this will give us is this value will give us a 0, this value will give us a 0, this value will give us a 0, and so on. So all of these values will give us a 0, and when we XOR them together later on, the rest remaining values, it's because all of the values that are remaining are 0, there is no way for us to get a 1. So, and we know that 0 XOR 0 is always 0, then we know that the answer of XOR is 0. In the case that 2i plus 1, similarly I can group all of these together in groups of 2, but there will be one left. Let's talk about the second case when the number of ones is odd. So in this case, when I'll be having one left, one left, all of the values will be giving a 0 when I pair them together. But since all of these values together give a 0, as we've talked about, there will still be a 1 left at the end. And when we XOR it with 1, we'll get a 1. And that's why I've proved this claim that whenever the number of ones in these bits is odd, so let's denote the number of ones by x1. So the number of ones in this out of these bits, whenever this value mod 2 is 1, then that means that if their collective XOR's value will be 1, XOR value. So this is one thing to keep in mind. So now let's try to boil down to what we have to calculate. So what is the minimum information that we need for us to calculate the answer? What do I mean by this? So what I mean by this is that we have to calculate, we know that there are n values a1 to an, and we have to calculate the XOR value of a1 to an. But and we are given 20 queries that we can ask. So we know that it's like literally impossible for us to calculate the entire value of a1, a2, a3, because if we had that, great, we would be XORing them those values, and we'll be able to get our answer. But we know that that's not the case. That's not that we won't be able to find that within 20 queries. So what is the minimum information that we need in order for us to calculate our answer? This is the answer that we have to calculate. So minimum information that we need, as we talked about, is, so for example, okay, let's talk about, suppose those numbers are 101, 110, 001. Okay, so these are the numbers, and we have to XOR of all of them. So this is a1, a2, a3. So n is 3 in this case. So suppose these are the numbers, and we have to calculate the value of this XOR of all of these numbers. So as we've talked about, the bits will operate individually. So bits will XOR individually. So the 0th bit will XOR individually. This sector will XOR itself, and this sector will XOR itself, and this XOR will XOR itself, and we'll have a value. So for example, in this case, the value is 0, because we talked about the number of ones. So because 1 XOR 0 XOR 1 contains two ones, we know that the XOR of these values will be 0. Because there is an odd one in this set, so I know the answer is 1. Because there are even ones in this set, we know that the answer is 0 again. So we figured out like a very good way for us to calculate the answer, and all of these bits will be operating individually on each other with each other. So let's move on, and so this is the example what we have to calculate. So we don't actually need the values of a1. All we need is for each bit set, for each bit, for the 0th bits, for the first bit, for the second bit, for each bit, how many ones are present. So if we know how many ones are present in each bit set, we will be able to know whether the bit of the answer is set or not. And how will we know that? If we talk about xi for a set a, for a1 to n, if we talk about xi as the number of numbers with the ith bit set. So for like for in this case x, let's talk about x of 0. X of 0 in this case is 2, because this bit is set, the 0th bit, we're talking about the 0th bit. So we have to calculate for all the values of 1 to 3, for all the values of 1 to n, which of the AIs, how many number of AIs have the 0th bit set. This is the value which denotes x0. So x0 is 2 in this case, because a1 has the 0th bit set and a3 has the 0th bit set, a2 doesn't has the 0th bit set. So we know that the x0 value is 2. Similarly, if we talk about yi, we know that yi is, we define yi as the number of bits with the ith bit is not set. So we know that y of 0 is 1, because only the a2 bit, only in the a2 number is the 0th bit not set. Similarly, if we talk about x1, so if we talk about x1, so x1 is basically the number of numbers in which the first bit is set, and we know that this value is 1 because only a2 has the first bit set and the rest are 0, and we know y1 is 2. Similarly, we know that x2, if we talk about the second bit, this set, so it has again two values set. So x2 value is 2 and y2 value is 1, and we know that the bits will be set in the answer only if the xi corresponding xi value will be odd. So in this case, this bit will not be set, so this will be 0 because it's even. This is odd, so this will be set. This is odd, this is even, so this will not be set again. So we know the answer is 1 0 0 1 0. And so we have basically sieved down to whatever is the smallest info that we need in order for us to calculate the answer. Now we just have to devise a way for us to either know the exact value of xi. Okay, so either we actually know the exact value of xi, then we'll be able to calculate the parity of xi, and whether that parity is odd or even will determine whether that bit is set in our answer or not. So this is the thing that we have to calculate, the parity of xi. So either we can calculate the parity of xi itself, either we get the parity of xi somehow, or we calculate the exact value of xi and then we know the parity by just dividing by 2. So let's talk about how to do this with respect to the queries that we're given. So we know that log 2 10 to the power of 6 is approximately equal to 20, and this is the same as number of queries. So this gives us an intuition behind that for each query that I make, I have to calculate some viable information that will help me determine at least one bit. So this is some intuition that it gives us. And the value of k is that is allowed is 1 to 10 to the power of 6. So this is important. So let's talk about in terms of if k equal to 0 was allowed. This is just an intuition. We just like this, the only reason why someone would XOR with k equal to 0 is purely on the basis of let's see what it gets us. Okay, so I'm going to define QAI as the query answer for k equal to I, and let's define so for example, if I give k equal to 0, then the answer will be QA0. So let's talk about QA0. So QA0 will be nothing but XOR, so there are n numbers. So A1 XOR 0 plus A2 XOR 0 plus A3 XOR 0 plus AN XOR 0. And this value will be given to us. So when we give k equal to 0 to that grader, so that they will return us with the value of QA0. In this case, they will not, because the value of k equal to 0 is not allowed, but we're thinking that k equal to 0 is allowed. So let's talk about what QA0 will give us. So there are two cases. We remember we talked about that when we XOR with 0, so in this case we're XORing with 0, and when we XOR with 0, that means that all of the bits before it are also 0. And when I XOR it something with, like, let's say 1 1, I'm going to assume that all the bits before it are 0 as well. Okay, so this is one thing to keep in mind. So let's move forward. So when I XOR it with 0, so there are two cases. Either the 0th bit, let's talk only about the 0th bit. Okay, so what we're thinking about is, can we use this 0 to calculate the parity of the 0th bits of x0? So can I know the parity of x0 by using k equal to 0? This is what I want to find out, some relation between qa0 and x0. Okay, so let's talk about what this relation might be. So what we have is a1 XOR 0, a2 XOR 0, a3 XOR 0 till an XOR 0. So for a number to be set for, so one thing to keep in mind is, for a number to be odd, its binary representation in the 0th bit will have a 1. If a number is even, then its binary representation will on the 0th bit will have a 0. So let's talk about these two numbers. This is 2, this is 3, and 3 is odd, 2 is even. And why is this the case? Because simply because we know that because this value is 0, this value is something 2 into 1. The rest of the values will have some value 2 into 1, 2 into something, and all of these values will be a multiple of 2, so that number is divisible by 2, and that's why I know that the modulus value of this number is 0. And because this is a one set, this number will always be 1, because this is the only number which is not a multiple of 2 which is added in the binary expansion. When I expand this number from binary to numeric value, to the base 10 value, from base 2 to base 10 value, we know that this is the only number which is going to contribute for a 1, and that's how we know that the modulus value of 3 is 1. So this is, so what I mean to say by this is, we can only look at the first bit and know whether a number is odd or even when I'm talking about base 2. This is true in base 10 as well. So for example, in base 10 we know that if a number ends with 0 2 4 6 8, we know that that number is even. Similarly for base 2, if a number ends with 0, then we know that that number is divisible by 0. If it ends with 1, we know that the number is not divisible by 2, and the henceforth its remainder with 2, it will be equal to 1. So let's go on. So let's talk about what QA0 represents. So QA0 will be nothing but A1 XOR 0 plus A2 XOR 0 till so on till AN XOR 0. And let's talk about two cases. So when the 0th bit of A1 is set, it will remain set. When the 0th bit of A1 is not set, if the 0th bit of A1 is not set, it will remain not set. So we talked about how if we're XORing with 0, that number remains the same. It doesn't get toggled, it doesn't get flipped. So it remains the same. So let's talk about this, only the 0th bits of all of these numbers. So let's suppose that A1 had the first bit as set, 0th bit as set. Okay, so 0th bit at set. So if we XOR it with 1, then whatever the number this might be, this will have the 0th bit set. Okay, let's talk about this. So if we have this case, that so we have only two cases, either this the first bit, the 0th bit of this number AI will be set or it will not be set. So let's talk about both of these cases. So in the case that this number is set, so whatever the answer, the XOR value of this particular interaction will give us, it will give us a number. We will have numbers over at this end. We're only interested in the 0th bit because we know that we are only concerned with the parity of x0 in this case. So let's only talk about the 0th bit in this case, and 0th bit will be 1. Okay, so in terms of the 0th bit is 0, so we'll get a number with this interaction, and we know that because 0 XOR 0 will be equal to 0, we know that this the 0th bit of the answer for this interaction will be 0, and all of these values are being plus. Okay, so what we have to find out is, you know how binary addition works, right? So if I have 0 1 and I add 0 1, I can just add this, and this value will be 2, and I can give this as 1 0. So what I mean by 1 plus 1 is equal to 2, and that's how I know that the 0th bit will be set or not. So what I mean by this is, if there is so all of these interactions will have some value. So what I'm trying to figure out is a relation between x0, y0 and qa0. So what my claim is that the value, the individual value of these XORs will represent something and will give us a clue for us to figure out the parity of x0. And what this will be is basically the number of ones that are being given from these individual interactions will be the same as the number of ones that are set in the original array, and that is represented by x0, since we're talking about the 0th bit. So the number of ones in this interaction, the number of numbers in which the 0th bit will be set when we add all of these numbers will be added. So it will be set, suppose this will be 1, if this is 1, the 0th bit of A3 is 1. So the number of ones that we get in this sum for the 0th bit will be the same as x0. So, and as we talked about, if we sum two numbers, if we sum some numbers in binary form, if we talk about one bit, if we talk about the first bit, if there are even ones, then that means that this value will be 0. If there are odd ones, then that means that value will be 1. So it's quite similar to OR, XOR, and we'll talk about later why this is the case, but this is very similar. It's for like because this is because of the relation between XOR and addition. So XOR and addition are related, but that's beyond the scope of this question. You don't need to get into a lot of detail about how they're related, but it's easy to see with a pattern that if I add one more one, if I add one more one, in this case, because there are odd ones, we know that we'll be left with a 1 and some value here. So it can be 1. Maybe it can carry over one more if we add like one more or one more. So but we're only talking about this case, and for the first bit, if we talk about the first bit, so if there are odd number of ones, then we know that this bit will be set, and in the addition. So similarly, if we talk about x0, if x0 is odd, then we know that the first bit will be set in the sum of this value because x0 is odd, and that means that x0 is basically equivalent to my qa0, because the addition of all of these values will be qa0. So that means because I don't know the value of x0, but I know the value of qa0, and I know that because of the relation between qa0 and x0, I can draw this correlation that they will have the same parity as we have talked about here in this case. So let's move down. Let's write it a bit mathematically. So let's talk about the relation between x0, y0 and qa of 0. So x0 plus y0 equals n, because the total number of numbers that we're talking about is n. So either the bit in the 0th place will have its bit set or it will not be set. In either case, the sum of these values will be n because they're exhaustive. So let's talk about Bij. Bij is basically when I write Bij, what I mean is that I'm talking about the ith bit in AJ. So AJ, A1, A2, A3 till AN, and I'm talking about the ith bit. I value will go from 1 to 0 to 19. to represent the 20 bits, because we talked about log to 10 to the power of 6 is basically 20. So this is the case. So let's talk about what answer of 0 will be. So answer of 0 will be all of these values, XORs of all of these values, B1 0, B2 0, B3 0, the 0th bit of AI, A1, the 0th bit of A2, 0th bit of A3, and these are all bits. And we're XORing all of these bits, and these bits will remain set. And as we have talked about how x0 will be equivalent to qa of 0, we know that x0 will be equivalent to qa of 0 because all of these values XORs. If they are odd, then the answer will be 1. If they're even, then the answer will be 0. In either case, their addition, if they're odd, will similarly be 1 if they're odd, and if they're even, then their addition will give us a 0 in that place. In this given which case, it will not be odd. So let's go around and do this with one example, what we've talked about. So let's XOR it with 0. Only talking about the first bit. So let's XOR it with 0. So all of this will have some value. I'm not interested in these values. I'm only interested about the XOR with these values. So if I XOR with 1 and 0, so I'll get a 1 in this case. If I XOR 1 and 0, I'll get a 1, I'll get a 1. So in all of these three cases, I'll get a 1. And so the value, I know that from the sum of these values, this QA will be odd. And rightfully so, because there are 3 ones, right? So the value will be odd. And that's why we can say that xi is odd, because x0 is odd, because we talked about how x0 is in equivalence relation with qa of 0, and x of 0, let's talk about x of 0. We can calculate x of 0 in this case. So x of 0, as you can see, 1 2 3, all of these three have the 0th bit set, so x0 is 3. And as we've talked about how qa is odd, that means that x0 is also odd, and we can confirm that x0 is odd in this case as well. So let's go about expanding this for several other queries for different bits, right? We talked about the 0th bit. This was an easy task for us to do. Let's talk about how do we expand from here. And this is the case for which k equal to 0 is allowed, but for the given constraints that we know, k equal to 0 is not allowed. So what we're trying to do is we're trying to take the basic observation that we can make from by using these things, and we try to fit them into the constraints. We'll talk about how we'll do that later. So let's talk about, so the next intuition that comes into mind is, let's send individual queries. Let's send individual bit set. So first, in the first example, I sent no bit set. Let's talk about if I send the first bit set. So this is my k1 0 0, which is 0. Let's talk about k2, which is 2. K1 is 1. Okay. So all of the bits. So the main idea is that between k1 and k2, all of the bits are set except one bit, and in this case, the first bit. So let's talk about what this value might be. So what the difference of these values might give us. Okay. So let's talk about what this value difference will give us. So what we'll have is, we'll have AI XOR K1 plus, so we have QA of K1 and QA of K2. Okay. So we'll have these values, and this will be nothing but A1 XOR 0 0 plus A2 XOR 0 0 plus A3 XOR 0 0, and so on till AN XOR 0 0. And similarly, for QA2, we'll have A1 XOR 1 0 plus A2 XOR 1 0 plus A3 XOR 1 0 plus similarly AN XOR 1 0. Okay, so let's talk about these two values. What I mean by this is basically we talked about how these individual bits operate on themselves independently. So the 0th bit of A1 will interact with the 0th bit of K. The first bit of A1 will interact with the first bit of K. So let's talk about what this difference will give us, QAK1 minus QAK2. So for each of these individual answers, there will be some answers. So let's write them individually. Let's subtract them individually. So we're talking about this set, we're talking about this set, we're talking about this set, we're talking about this set. Let's talk about each of these set individually. Okay. So because all of the numbers in, let's talk about A1 XOR this value, because all of these numbers are all of the bits of K are same except for one bit. All of the XOR values for all of the bits will be same. So for example, in the first bit, Suppose A1 has the first bit as 0, okay, first bit as 1, 0th bit as 1, and in both the cases of K1 and K2, the 0th bit value is 0. So we know that this value will give us a 1 here in the 0th bit, and we know that this value will also give us as 1 in the 0th bit. Similarly, if we talk about A2, if let's say that A2 will have the 0th bit as 0, and this value is basically, so whatever be the value, because it's XORing with the same value in the 0th bit, because K1 and K2 is, that's essentially because of the way that we designed K1 and K2 to be. K1 and K2 only differ in the first bit, the 0th bit, the second bit, the third bit, all of the bits are 0 apart from the first bit. So because of this, or no matter what the value of a1 on that other than 1 bit, the first bit is, the XOR value will always be same, and they'll always subtract to give a 0 in that place. So that means that whenever I subtract this value, it will have the 0th bit as 0, because the number of ones that I get from this, suppose that I get a 1 from this, I'll also get a 1 from this in the 0th bit place. If I get a 1 from this, I'll also get a 1 from this in the 0th bit place. In this case, I'm not getting, because the 0th bit is 0, and 0 XOR 0 is 0, 0 XOR 0 is 0. In case 1, 1 XOR 0 is 1, 1 XOR 0 is 1. So it'll always get subtracted within the first bit. So the first bit will always give us a 0, but now the 0th bit will always give us a 0. But now let's talk about the first bit. Okay. So what this first bit value inculcates, okay? So the first bit value will depend upon how many number of ones were set and how many number of zeros were set in the first bit, and that is what is of importance. So let's talk about the first bit again. Let's shift this example to the first bit. So suppose the first bit of a1 is 1. Now let's talk about these two cases. So 1 XOR 0. Let's do this a bit more neatly. So let's talk about in this case. So suppose we had this a1 XOR 0 0. Now we have this a1 XOR 1 0. Suppose that a1 had the first bit as 1, and this is something no matter what. Let's say it's 0. Okay. So let's talk about the first bit. So first bit gets interacted with k, and the first bit of k gets interacted with the first bit of a1, which is 1 in this case. So 1 XOR 0 will give us a 1 in that bit place. We're talking about the first bit only. We'll have some value over here. We're not consider about this value. So, and in this case, it will give us a 0, because 1 XOR 1 is a 0. So as we talked about that, the bits get flipped. We talked about how the bits get flipped when they're 1, when they're XORed with 1. So we know that for QAK2, what the value is. So how many bits are set for QAK2, and this first bit will be set only when the A1 will have the first bit as 0, and this is how we get the correlation between x of 1 and QAK1 and QAK2. So let's talk about what this correlation is. So basically what we're talking about is this difference, QAK1 minus QAK2. What we're trying to do is we're trying to draw some correlation from our now query and from our previous query, and let's see if that subtraction gives us something useful, because all of the bits are set. All of these values subtracted will give us 0, and the only bit that will matter is the first bit in this case that we're talking about. And so let's talk about when this value in the first bit will give us a 1, and because we're XORing with 0, this value will give us a 1 only when this value a1 will have a 1 in this place. So a1 had a 1, and that's why this value gave a 1. Now a1 had a 1, and because of this, when we XORed it with k2, that value gave us a 0. So the second value, when we XOR it with k1, so a1 XOR k1, which is 0 0 0 in the first bit, and a1 XOR k2, which is a 1 in the first bit. We're only talking about the first bit. So this value will be 1 if and only if a1 is 1 in that bit set. That bit is set. This value is 1 only it's not set if that bit of a1 is not set, because that bit will be reversed, that bit will be flipped, and that flipped bit will only be 1 if the initial bit was 0. So 0 will get flipped into 1, and that's why I can say that this bit initially was not set of a1. And what these values symbolize is nothing but the value of x1 minus y1. So as you can see that the first value will give us a 1 for the A1 bit in the ith position as set, and that value is denoted as x1. And when we subtract this value with the second value XORed with k2, so we know that A1 XOR k2 will give us a 1 only when the value of A1 for that bit is 0, and that is nothing but the value of y1. But this will only start from the first bit, so we can this change will only happen from the first bit, because all of these previous bits that we talked about, in this case there is only one previous bit, the 0th bit. This will always be 0 in this case. This will always be 0 in the subtraction, because they'll all get subtracted. The number of ones in the 0th place in all of these XOR will be same, because all of these bits are XORing with 0. So we know that this will be 0, so we have to divide it by 1. So we have to divide it by 2, so that we only talk about this plate, and this value will be the same as QAK1 minus QAK2. So this is one relation that we have, and another relation that we talked about was x1 plus y1 is equal to n, because the total number of numbers is n, and adding these two together, we'll get the value of x1. Two variables, it's two equations. We know the value of QAK1, we know the value of QAK2, and that's why we'll calculate that's how we'll calculate the exact value of x1. And when we calculate the exact value of x1, we can calculate the exact parity of x1. So that will be of help. So now that similarly, say we talked about x1, so let's try to write a general formula. So for each of xi plus yi will be equal to n. Now let's talk about the second equation, and this second equation is going to be xi minus yi divided by 1i, because all of the bits before them will be 0, because their subtraction will be 0. And since we're only concerned about whether this number is odd or even, we only have to talk about this bit, and when we talk about this bit, we have to remove all of the bits that were before it, because they're already 0. We can easily remove it and check out whether this number is odd or even, and we'll get this value, and this value will be equal to qa ki minus qa k1. So this is not I minus 1, this is k1, because we've said, so the first query that we send was 0, second query was 1 0, third query that we will send is 1 0 0, the fourth query will be 1 0 0 0, and we'll always subtract with 0, so that all of the bits will be so for if we consider these two cases, only these bits are different. If we consider these two cases, only this bit is different, all of the other bits are different. The same. If we consider this case, only these bits are different, all of the bits are same, 0 0 0 and 0 0 0. So we always have to subtract QAK1 minus QAKI. I've written this wrong. So QAK1 minus QAKI will give us xi minus yi divided by 1 left bit shift operator I. So let's talk about how to use this observation. So we found this observation to be quite useful. So let's talk about how this observation can be transformed into the given constraints, because at the first place it's not allowed to give k equal to 0, which we are already giving. So what we want to talk about is how to fit how to change k's to fit the constraints using the observation that we made. So the key observation is we made is um, between two queries, if only one bit is different, their subtraction can provide valuable information about xi. Okay, so let's expand this. Okay, so let's talk about the next biggest number that we can give, right? And that is k equal to 1. So what happens now? So our answer will be qa of k1 will be a1 XOR 1 plus a2 XOR 1 plus a3 XOR 1 and so on till an XOR 1. And as we talked about, when we XOR with 1, the number of bits that will be set will be that the number of zeros that were here. Okay, so if a1 had a 1 in the 0th bit, then that answer will give us a 0, not 1, because this bit will get flipped into 0. And if you want the flipped bit that we're actually concerned about, so this will be something we're only concerned about the 0th bit. So, and if you want this value to be 1, then this value is going to have to be 0. So the 0th bit will have to be 0 in A2 if this bit is 1. Okay, so we know that the number of ones that we get is for each of these individual interactions is originally going to have to be 0 in this A3, and which is nothing but yi. So we can say that yi will be equivalent to qa of k1 y of 0. Okay, so we're talking about the 0th bit. So we know that y of 0 will be equivalent to qa of k1, and because we know that x0 plus y0, and we talked about that the number of ones is the sole contributor in the 0th bit of whether this number is odd or even. So we can say that qa1 is equivalent to y of 0, and the second relation that we know is x0 plus y0 is equal to n, and henceforth we know that x0 is with correlation is equivalent with qa1 plus n. So this is the difference. In the previous thing that you remember, we wrote that x0 is directly with correlation equivalent with qa k1, but this is not the case. In this case, x0 is directly correlated with qa k1 plus n. So this is the first thing that we'll send. What is the next query that we'll send? This is important. So what is the next query that we might send in this case? And the next query, that because the initial query was 1 and our initial observation was that only if one bit is different, then we can draw some good correlations about that bit on which that k value is different. So we chose k1 equal to 1. So that gives us an intuition to use k2 as 1 1, and the next k3 will be 1 1 1 1. So what happens in this case? Only so let's talk about these two. So these two bits will be the same for this case, the same for this case, only different in this case. Okay, let's talk about these two. So these two will be same in this, and will be different only in this. So if we talk about the subsequent two queries that we're giving, then these two queries will have all the bits same except the ith bit. So again, we can draw a correlation between these, and I can write a general formula expanding from the previous one, which will be, so if qa k of I is given to me, is what I'm figuring out. So no, one second. So if I want to draw, but the thing to keep in mind is that x of I minus y of I, again we're going to divide by one left exponential. We're going to remove all the right one bit I bits for this, because all of these values will again give us a 0, because 1 XOR with 1. So all of these values are same, so the same logic holds. Previously it was 0, but now all of these right values are 1. So then again it doesn't change any much, because the individual subtraction will give us a 0 for each of these values. So this value will be nothing but qa of k of I minus 1 minus qa of ki, because the 0th bit is not set in k of I minus 1, and this will be the sole contributor of all the ones in the place, and this will be the sole contributor of the ones on that bit's place, on the zeros of that bit place. So this value corresponds with this value xi, this value corresponds with this value yi, because xi, the number of xi's will be correlated with qa of k of I minus 1, because qa k of I minus 1 will have this ith bit as 0, and qa of k of I will have the ith bit as 1. So for example, in this case k3 we have 1 here, and for k2 we have a 0 here, because the 1 didn't reach this value. So we know that this value will be 0, so I minus 1th value will be 0 in this bit's place, and because this bit's place this value will be 0, and I'm XORing with ai. So if it's a 0, it will remain a 0. If it's a 1, it will remain a 1. So the only contributors of 1 will be when it was initially 1, the ai on that bit was initially 1, and that is represented nothing by xi. this is in the case for QA k of I minus 1, but for QA k of I, for this bit will be 1 in this place, because the ones have reached this bit place. And when we subtract this will be 1 only when the initial bit was 0. So if the AI was 0, then if I XOR it with 1, that value will give us a 1. So the number of ones that we have for this place will be dependent on how many zeros we had in the previous place, and that is represented by nothing but xi by I. So this will be our correlation that we're going to draw. And that's how we have actually expanded our initial observation to fit the constraints that are given in the question. So let's talk about a bit about pseudocode. So the pseudocode goes as follows. So firstly, we get QA of 1 for k1 equal to 1. And we know that the parity of x naught will be directly correlated or with the equivalence relation of QA of 1 plus n. Then we get QA of 2 for k2 equal to 1 1, and we know that x1 minus y1 will divided by 1 left bit shift operator I will be nothing but QA of 1 minus QA of 2. So previous subtracted by the right now ith bit. So and so on and so on and so forth. So for QA of I, k for k equal to I with the I ones, so we know that xi minus yi divided by 1i is equal to QA of I. So this is wrong. So QA of I minus 1 minus QA of I. So for example, in this case, it was 1 minus 2. So it's QA of I minus 1 minus QA of I. And we talked about, because this is correlated with this, because xi is the number of xi is the number of ones in that ith bit place. Because they're XORed with QA, the 0 in QA of I minus 1, they'll be correlated, and the y's will be correlated with QA of i's because they're being XORed with 1, and the bits will get flipped. So initially they had to be 0 in AI, and that is represented by yi. And because all of these bits from the ith bit onwards, from the right of ith bit, will be 0, so we have to subtract, we have to remove all of these bits and then talk about these bits. So find all of so we have all the parities of xi's. So find all the parities of xi's for I from 1 to 20, and for all of i's for which xi is odd, we add answer. We know that that bit is set in the answer, so we add 1 left bit shift operator I. We set that bit in the answer, and this is the pseudocode. So let's go on and see the implementation for this. Okay, so this is an implementation, really small. So what we do is initially is so int main. So I've defined LL by long. So what we do is basically we firstly take t test cases, we say in t, then we write while t minus minus, we take that value n, the number of elements, and then we output 1. So as you can remember, the first thing that we output is 1. So we output 1, and then the grader gives us a value. We read that value, and we know that this is the QA of 1 value, and we know that n plus y is, if n plus y is actually correlated with x of 0, and if this value is 1, modulus 2 is 1, then we set the first 0th bit in the answer, and then we're going to repeat this 19 more times. We're gonna set the ith bit again. So as you can see, this is not an equal to sign, this is a plus equal to sign. So I'm actually adding one more set bit in our initial value. Initially a was 1, so 0th bit was set. Now the first bit is set and the 0th bit is set. For the next iteration, the second bit will be set, the first bit will be set, as well as the 0th bit will be set. So as we talked about, so 1 1 1 1 1 1, all of these values I'm sending, and then I'm gonna output this value, and then the grader is gonna give me the answer for this value. And what we've done is basically from the value of xi plus yi is equal to n, and xi plus yi, xi minus yi is nothing but that QA of I minus 1 minus QA of I divided by 1 left bit shift operator I. So we, using those two variables, two equations, this is the equation that we'll get for xi is the exact value, and we model it by 2, and then if we get a 1, we set this bit, and we set y equal to x. So y is nothing but the previous iteration value that we got, and x is nothing but the right now iteration value that we got. So the right now, whatever the grader has given us for this for the a that we've given it for the ith bit set, for I to all of the bits towards the right set, so that value is represented by x. For the last iteration, whatever value it was given to us, that is represented by y. And for all of these values for which the grader, whatever the value that the xi is odd for, we set that bit in the answer, and then we see out the answer. And so as you can see, this is a completely AC, and that too 0 seconds. So that was it for this question. I hope you liked the explanation, and please remain seated for like much more questions like these, and all the best for the cook-off that is coming. So have a good time.